Whew! Today is the day we start talking about the derivative rules. No longer are we going to be shackled by those definitions. Before we begin, though, let's take a review of some problems for us that we're going to see again. For example, like in number 1, it says right here, you want to write the equation of a tangent line. You're going to be doing this your whole life in mathematics, so just go ahead and get used to it. And they want to find us the equation of the tangent line at x equals 3. So if I look here, remember the two things that we need a point and we need the slope. Well, the point is pretty easy. That comes from the value itself. That's its f of 3 is 2. That's the point. And we don't typically write points that way. We typically write it as 3, 2. The slope, remember, that comes from our derivative, d. So our slope here is saying the slope at 3 is the derivative at 3, which is 1/2. So we have our point and we have our slope. To write the equation of our tangent line, we're going to use our point slope form, y minus y1 equals m, x minus x1, and that gives us y minus 2 equals 1/2 x minus 3. And there is the tangent line right there. There's the equation of our tangent line. Very easy to do. Alright, the next question says, the given limits represent the derivative. Now we've done these before, and we're going to see these again and again and again because it's how the AP likes to mess around with us. The given limits represents f prime of c for some function number c, and we want to find f of x, the function, and we want to find c. Basically, when they say c, remember they're just looking for that x value. So if we look here, this is our definition. This comes straight from our definition, which remember begins as the limit as h goes to 0, and what we're really just looking at is this first part right here, this f of x. Remember, it's still minus f of x over h. So I just look at that f of x, and that comes right over here, sine of pi over 2. That's what I'm looking at. So I know that f of x has to be my sine function, but we're talking about a function in terms of x, so we just replace that 1/2 with pi over 2, with x. And that's not saying that pi over 2 isn't anything. That's our c value. That's the x value we're looking for, and that's going to be 1/2. And there's our answer right here. For part B, you might recognize this as the alternate form of the derivative, and the alternate form says that limit as x approaches c of f of x minus f of c all over x minus c. And again, I'm just looking at that first part here, sine of x squared, which in this case, is x cubed. Oh, I love sine functions, I guess. So our function here will be x cubed. And we're looking for c. Well, we can just look at what we're approaching here. And c is 3. And there it is. Very easy to do. Alright, the AP likes it. You'll see this on the AP test. Alright, so today we're going to take a look at the power rule for derivative. Now, most of us have been kind of looking at, we've been doing the definitions for a while. And you might have recognized a pattern, especially with power functions. We have what's called the power rule. This works for what we call power functions. And a power function, in case you forgot, is just something x to the n. That's a power function, where n has to be a real number. So our rule is the following. If we have f of x equals x to the n, our derivative rule, f prime of x, we just drop the n down, and we get x to the n minus 1. We just subtract the power. And that's our rule. This is the shortcut for it. Okay, we're going to spend this whole unit learning shortcuts. Right? Now, other derivatives we will need to know, the simple trigonometric ones. Okay, you have to memorize these. We're not going to work proving these just yet. Now, I'm going to write these in Leibniz notation. Remember, this is Newtonian notation. But I'm going to say the derivative of sine of x with respect to x. So the derivative of sine of x with respect to the change in x. That's really what this means. The derivative of the sine of x with respect to the change in x is just cosine x. And the other one is, what's the derivative of cosine of x? So the derivative of cosine of x with respect to the change in x is negative sine of x. And we can kind of see these if we kind of graph this a little bit. So let me just show you this real quick. Let me graph the sine curve right here. 0, pi, 2 pi. So there's our sine curve. So there's y equals sine of x. Now we had one on our last homework where we had to graph a derivative. Well, if I'm graphing the derivative, remember the derivative is the slope of it. Here's 0, pi over 2. The first thing we look for are our critical numbers. You might remember that. There's my critical number where the slope is 0. There's my critical number where the slope is 0. And this just happens to be at pi over 2 and 3 pi over 2. Like so. Those are our critical numbers. Next, we look at the slope. Well, the slope between, you might remember this from before, positive slope, negative slope. Who's the slope in the middle, right? Slope is 0. So between 0 and pi over 2, the slope of sine is positive. So it's going up. But then after pi over 2, it's negative. So the slope is positive, but remember, it's starting off like at a slope of 1. So starting up like up here at 1, it's going down, crosses 0, and then between 0 and 3 pi over 2, the slope is negative, so it's below the x-axis, but it goes back to 0. And then afterwards, at 2 pi, the slope is about to 1. And if you notice, if you're good at this, you recognize this is just the cosine of x right there. So you can kind of see just by looking at the slope here. All right, we'll talk more about this later on. All right, so other forms for writing the derivative, we talked about this before. You had Newton, he liked f prime of x, y prime of x, stuff like this. We had Leibniz liked this dy dx. We really are going to like this one, you'll see that one. And then you have that fancy one that mathematicians don't tend to use, but computers nerds do tend to, the change in y, the derivative of y with respect to x. And you'll see this one too. We'll talk about this later on. Dy dx at x equals blah blah blah. This is basically looking for a slope, and physicists actually use this one quite a bit. We'll see that today too. Okay, so let's take a look down here at our rules. Okay, so we have this function f of x equals x cubed. Well, we want to take the derivative. So my rule says, well, if I want to find the derivative f prime of x, I drop my power to the front, put the x there, and I just subtract. Well, what's 3 minus 1? Which is 2. And there's our answer. So we drop that power down and we subtract 1. And there's our derivative. Well, what if we have something like the square root of x? Well, this is not a power function. Neither is the next one. These aren't power functions right here. So the question is, well, how do we take care of them? Well, we write them as power functions. In other words, we just give them a power. Well, this becomes x to the 1/2. And now if I take the derivative, I'm going to bring that power down, and that becomes y equals 1/2 x. Now be careful, if I subtract 1 from 1/2, I get this negative 1/2. Now, there's one rule that we don't like. No negative exponents. Okay, you cannot have a negative exponent here. So that x to the 1/2 right here, this little negative 1/2, has to go to the bottom. And how do I write that? 1 over 2 is already on the bottom, and the x to the 1/2 goes on the bottom. Now, we're going to see the square root of x so much, you just might as well memorize that one. Oops, remember, I called it y, right? What should I call it? I shouldn't call it y anymore because it's a function. So I can either put y prime or dy dx. Now let's take a look at why we like dy dx here. Okay? When you were a young lad in Algebra 1, you said the slope was change in y over change in x. Well, this is the slope in 2 points. This is a secant line, and it needs 2 points. Well, the same thing in calculus, we call it dy dx. The difference is, by changing the delta y delta x to dy dx, this now becomes a tangent line. And it is the exact slope in 1 point. Now, another thing that we call this is called the average rate of change, because it takes 2 points. We sometimes call this the average rate of change, or AROC. At 1 point, we call this the instantaneous rate of change, or IROC. AROC is average rate of change, 2 points. IROC is instantaneous, so we're finding the slope at exactly 1 point. Now, ideally, we want these to be equal to each other. And we're going to talk a lot about that this year. All right, in the meantime, let's talk about number 3 right now. This says find the derivative. We want to find the derivative of 1 over t to the 4th. But again, this is not a power function. So I'm going to make it a power function by just bringing t up to the top and makes it negative 4. And therefore my derivative f prime of t, what's my rule? Drop that power like it's hot. So that's going to become negative 4t. And if I subtract 1, we get negative 5. Again, no negative exponent, so I write my derivative. Whoop, I should use a t, not an x. If you make that mistake, use x instead. The AP are going to be like, oh look, they can't spell the letter t. You'll be okay. So we get negative 4 over t to the 5th. And there's our answer. So remember, this rule only works for power functions. So if it's not a power function like number 2 or 3, we make them a power function by writing them as such. Alright, so let's take a look at number 4. Now number 4, look at this. We have 4 functions here. So when I want to take the derivative, I just do each one separate. The first one, I'm going to drop it like it's hot. This becomes 12x. If I subtract 1 from the 3, I get squared. Minus, notice when I'm dropping it down, I'm multiplying. This becomes 10. 2 times 5 is 10x. Let's see what the power is. Minus 1. So I put the 1 there. If you don't put the 1 there, you're okay. But I want to talk about this one here, 7x. Ready? There is a 1 here if you don't forget about it. So if I drop down that 1, of course, we're going to get plus 7x. And be careful, when you subtract 1, we will get 0. Plus, now be careful, this is a tough one. What would be the derivative of 3? Well, we saw this a while back, a few days ago. This is our constant rule. This is just a constant. Okay? 3 is a constant. And what we say for a constant, well, think about this. This is just the line y equals 3. The slope, 0. So this is just 0 here. Now, of course, you don't have to show all of this work for this problem. We really just want to get straight to the answer, which is just 12x squared minus 10x plus, be careful, anything to the 0 power is 1, so that's just 7, and don't put the plus 0. And there's our derivative. Now, if you notice for power rules, really we just bring each power down 1. A 3 became a 2. A 2 became a 1, right? 5, okay, let's take a look here. Again, these are both not power rules, so we have to get them at power rules. For number 5, we're going to split that fraction that we did earlier in another problem. We're going to split the fraction here. Now you will see one of these on the quiz or a test, I guarantee it. And this is the one you're going to miss. We get y equals, this becomes 5x to the 5th over x minus 3x to the 4th over x plus 4 over x. Now you're going to eventually not show all of this work. You'll go straight to this next part. That's our goal here. This just becomes 5x to the 4th minus 3x cubed. Be careful, bring that power up, plus 4x to the negative 1. And then when we take those derivatives, right, we're going to drop all of these powers down into the front here, that negative 1 included, right? And this becomes y equals 20x cubed minus 9x squared minus 4x, be careful, subtracting 1, negative 2. But again, right, no negative exponents. Now if you notice, I just took my derivative, so I better put my prime there. So we need that prime. Need y prime, tell me it's a derivative. So y prime would equal 20x cubed minus 9x squared. Be very careful. Minus 4, the x squared only goes under the 4. You're going to be tempted to put that x squared underneath everything. It's not. And you do not have to write this as a single fraction. You leave that alone. Okay, now if you notice, sometimes I use a prime, sometimes I use dy dx. Does it matter which one I use? Absolutely not. Sometimes I use dy dx, sometimes I use a prime. You just want to make sure you show that it's a derivative. Like for this one, I probably should have said this is dy dx. It means the exact same thing. Okay, just make sure you have those. Alright, now for number 6, to get this into power form, we must expand. Okay? So let's go ahead and do that. We would get f of x equals 9x squared plus that 6, that becomes 12x plus 4. And then just taking the derivative, remember this is a 2, bring it down. There's a 1 here, bring it down. And there's really an x to the 0 if you want to think about why that becomes 0 here. We get f prime, don't forget your prime, 18x plus 12 plus, like I said, if you pretend like that's x to the 0, 0 times 4 is just 0. So there's our derivative right here. And you can put a 1 there if you want. You could put x to the 0 here, but remember, x to the 0 just is 1, so we don't really need to put anything here. Alright, so take a look at those. If you have any questions, definitely please ask. Okay, bye.